Okay, welcome all. So today to another lesson that will be on the numerical of doubly reinforced beam. Okay. So first we will see some little bit of concepts that are required for the numericals, and then we will start our problem solving session. Okay. So first we can see a stress strain diagram of a doubly reinforced beam. Okay. So see what all learnings we can take. You can see here it is the stress diagram. Okay, this is the stress diagram. So what is the change from a singly to doubly? We have entered here the rebars at the compression zone also. Okay, so what is the first change? So the first change in the strain diagram, there will be a strain coming that is known as ESC. Okay, strain in steel in the concrete section. Okay, so how can we get that? You can see here it is written from the similar triangle concept. uh, we are getting ESC is equal to 0.0035 into multiplication XU minus DC divided by XU. Okay, so for designing, XU will be equal to XU limiting. Okay, XU will be equal to XU limiting, and you all know XU limiting can be calculated from K into D. Okay, I am writing it here also. XU limiting can be calculated K into D. So what is DC? So as in the bottom section you can see D naught. So D naught is the effective cover. In the same concept, the DC is the effective cover in the compression zone. Okay, so this is the effective cover from the compression zone. So if it is also not given in the numerical, we will consider it as 50 only. Okay, 50 only as the cover. See, in one thing you can derive it from here. If it is a singly reinforced beam. Okay, if singly reinforced beam, there is one lever arm. Okay, there is one lever arm, but for doubly reinforced, there will be two lever arm. Okay, see what is the two lever arm. You can see here in this stress diagram, the lever arm number one is D minus 0.42 XU. You have seen it previously only in singly reinforced. The another lever arm will be D minus DC. See the lever arm 2, D minus DC. Okay, it is from the middle of this bar to the middle of the tension zone bar. Okay, so this is the lever arm 2, and the lever arm 1 is, you can see, from the combined force of compression, okay, to the tension reinforcement middle. Okay, so what other thing it is coming from here? So you can see the strain value we have calculated in this way by the similar triangle concept, 0.0035 XU DC divided by XU. Okay, so the combined force you have seen for the compression is 0.36 FCKB into XU. Previously we have seen it, but now the combined force uh, for the reinforcement or the rebar in the compression zone will be this one. Okay, so this one C is equal to FSC into ASC. So how it is coming? So C is the force. Okay, so we all know stress is equal to force by area. So we can write it as also this force is equal to stress into area, stress into area. So this is only written FSC is the stress and ASC is the area. Okay, so this one is the new thing, we can get it from here. Let me check what other thing can we get from here. Okay, only this part only. Okay, all other thing are same. See, if you want to know how this value is coming, you can see it here, that similar triangle we are taking AOB and COD, means AOB and COD. Okay, so AB by AO, AB by AO. Okay, so perpendicular by base, and this small diagram also CD, sorry, base by perpendicular, CD by OC. Okay, so this OC value is coming, OC value is coming, you can check it here, XU minus DC. Okay, how it is coming, see here, this from this to this it is XU, depth of the neutral axis, and this part is DC. So this part, this small part will be XU minus DC. So it is XU minus DC. Okay, and this total, if you take this total, this is XU. So here you can see this AB is equal to 0.0035 divided by XU, it is totally XU. Okay, is equal to epsilon SC. You can see it, this one is the epsilon SC CD, epsilon SC divided by XU minus DC. This small part is XU minus DC. Okay, from this we can derive the formula of stress in steel. Okay, so here also we will calculate XU, limiting everywhere will be same, but the XU formula changes here. So we are equating compression is equal to tension, as because in the neutral axis both will be same. So see one thing, this part you know, for the compressive strength of concrete we get it 0.36 FCK B into XU. Okay, this part is plus FSC into ASC. This part is the force for the steel, we see it here only. Okay, this part minus we are doing subtracting 0.45 FCK minus AC. Why we are subtracting it? We are subtracting it as because, see, previously in this part this was fully filled with concrete. Okay, so this, when we have entered these rebars, so some amount of concrete we have taken it out from here. Okay, and replaced it with rebars. So this subtraction is the amount of concrete taken out. Okay, 4.5 0.45 FCK ASC, and this part is the same, the tensile strength of the steel. Okay, so by deriving, by calculating it, we get this formula XU is equal to 0.87 FYAST. So this was previously, the addition is minus ASC bracket FSC minus 0.45 FCK. Okay, divided by 0.36 FCKB. So this part and this part is same. So addition, new addition is the this part. Okay, so this is the XU formula, neutral axis, depth of neutral axis derivation formula. Okay, so we will see the formula of moment of resistance in the tension side. So moment of resistance in the tension side is 0.87 Fy. So we know that moment of resistance formula is as force into lever arm. Okay. So this part will be the same, as there is no change in the tension zone. 0.87 Fy AST D minus 0.42 XU, but in the compression side there will be change, as because we have entered rebar there. So see, 0.36 FCK BXU D minus 0.42 XU, this was same. Okay, plus, so what is the change now? We will see FSC into ASC minus 0.45 FCK, and this is, you can see that this is the combined force. Okay, so see, it is how it is coming. You can see that FSC ASC, this is the force. Okay, if you multiply these both, this is the force, and minus we are doing 0.45 FCK FSC. So this one is the concrete amount taken out. Okay, so this both combine the force. Okay, so see FSC using it. Okay, yeah. So FSC AC minus 0.45 FCK into the lever arm. Okay, so this is one is the force into lever arm. Okay, so same thing also, this one is the force and this one is the lever arm. Okay, so moment of resistance in the compression zone. So there is another image in detail, you can get it from here. So the main thing what is why we are doing doubly reinforced. Okay, why we are doing doubly reinforced. Singly reinforced was also good. So you can see here, if we calculate bending moment design, okay, design, and if we calculate MR balance, moment of resistance balance, or limiting, what you can tell same thing. If bending moment design is greater than bending moment balance, okay, so we have to do some extra thing, as because your original force is coming more than the beam ultimate limit. So we are going to do the doubly reinforced. You can see it here, bending moment design is equal to bending moment balance plus bending moment extra. For this extra part we are doing the doubly reinforced. Okay, so you can see it here, what we are doing. See, here is written AST1. This is the previous case. Okay, so you can just consider it as a singly reinforced. Okay, so this AST1 previously considered, plus, see here, plus is given. Okay, plus now what we are doing, for this bending moment extra, we are providing AST2, more steel in the compression zone as well as more steel in the tension zone as well as more steel in the compression zone. Okay, so this the formula of bend ASC and AST2 you have to get, as because AST1 we know, okay, previously, but in this case we have to know these two formulas. Okay, so you can see it here, how we can get. See, bending moment resistance, bending moment extra. Okay, so bending moment extra is equal to how the moment is derived, the force into lever arm. Okay, this is the force into lever arm. So how we can get the ASC, we will bring this one, we will bring this part and this part to the down. Okay, to bottom. Okay, same here also, if you can see, bending moment extra is equal to the force 0.87 AST Fy AST2 and the lever arm D minus DC. Okay, so this is the lever arm 2, this is the lever arm 2. Okay, lever arm 1 was D minus 0.42 XU. So from here AST2 can be calculated, everything we will bring down. So let's check, and you can see here also the moment of resistance balance, the formula 0.87 F by AST1, and the lever arm for the singly reinforced was D minus 0.42 XU. Okay, so see, all the formulas are given here. AST1 is equal to B, bending moment balance or limiting, mu limiting, you can tell it as mu limiting also. Okay, okay, so mu limiting divided by 0.87 Fy D minus 0.42 XU. So this is the AST1. AST2 you can see it is coming from the moment of resistance formula. AST2 is equal to bending moment extra divided by 0.87 Fy D minus DC, and ASC is bending moment extra divided by the moment of resistance. Okay, FSC FSC minus 0.45 FCK D minus DC. Okay, and here the FSC, how the FSC will be calculated. FSC you don't have, okay, everything you will have. So how the FSC will be calculated, we have to first calculate the strain, ESC, okay. So 0.0035 XU minus DC divided by divided by XU, where XU will be equal to XU limiting. And how you can calculate, mainly in the problem you can see that there will be a chart given epsilon SC and FSC. For this value will be given, okay. If your value is not given, the two value will be given, you have to find the middle one. Then you have to do the interpolation, okay. This value, this value, this value, this value will be given, you will get a value of this middle one, FSC, epsilon SC, from this one. So you have to do then interpolation. Okay, we will see how to do the interpolation also. See, every formula is covered, okay. So you can write here one formula that will be important. If you have forgotten how to calculate mu limiting, see here, mu limiting, the formula is q b d square, okay. So the q depends on the grade of steel given, okay. See now how to do the interpolation. So if you say this value is strain value and this value is given as stress value, means FSC, okay. So how you will calculate, see, you will find the formula that is given epsilon, okay, SC is equal to 0.0035 plus XU minus DC divided by XU, okay. So from this formula you will get the value of C here, okay. This C you have to find FSC. So then you have to do the interpolation. How we will do it, let's say this value is as X, okay, for us. So X is equal to, you see, first this one P plus the now here this value minus this value divided by this value minus this value. So you see, B minus A divided by Q minus P, okay, into this minus this, C minus A, okay. So this is the interpolation, you will get this value, you will get the X value, okay. So this is the interpolation, how to do it. You can see here a chart is given, okay, a chart is given for this. The strain is given, that is, and the stress is given, okay. For this is for FE 415 and this is for FE 500, okay. So this will be given mainly in the numerical when you do it, okay. So we are starting a numerical. See what, calculate the moment of resistance of a doubly reinforced beam of size 420 into 750, okay. 420 into 750 is the dimension. Reinforcement provided on the tension side is 6 number 25, okay. So 25 mm dia bar, and on the compression side 5 number 20 mm dia bar. Use M25 concrete FE 500, okay. So moment of resistance, so for that what we have to calculate, first we have to calculate XU and XU limiting, okay. After that we can do it. So let's check. XU limiting is equal to K into D. So we will do it here. XU limiting is equal to K into D. So now for FE 500, see, for FE 500, K is equal to 0.46 into D. Let's check what is the D. D is 750. So 750 minus 50. So it's coming as 322 mm. Now we will calculate XU. See here, the XU formula is given. See, the XU formula is given here. Okay, so first, how you can remember, just write first the doubly reinforced, singly reinforced thing, 0.87 Fy AST, and there was divided by 0.36 FCK B, okay, minus ASC, just check once, ASC FSC minus 0.45 FCK. So this part only we have to remember. FSC minus 0.45 FCK. So we will put the values here. Okay, so see here, we have to calculate the FSC. Okay, so first we will find out the epsilon SC. Epsilon SC is equal to 0.0035, okay, plus into XU minus TC divided by XU, okay. So is equal to 0.0035 into, so we are taking XU as XU limiting. What thing we can do, we will not take XU as XU limiting, we will just assume, okay, FSC we will assume it. So you can write it here, just write it one line, assume FSC as 350, okay, we are assuming as 350 Newton per mm square, we are assuming it as 350. Okay, so now we will check it also, the assumption we have done FSC is 350 is correct or not. Okay, so 0.87 Fy is 500, okay. AST we have to calculate, so AST is given as 6 bar 25 dia. So AST we will calculate it here. AST is equal to 6 bar 25 mm dia. So its value is coming as 2945 mm square. So ASC we will also calculate. So see, 5 bar of 20. So 5 bar of 20. So it's coming as 1571 mm square. Okay. So let's continue. So we will put it here, 2945 minus ASC is coming as 1571. Okay, FSC we have assumed it as 350. Okay, 0.45 into FCK. So FCK is M25. Okay, so it's 25 divided by 0.36 into 25 into V. Let's check. V is 420. 420. So give a minute, I will calculate it. 350 minus 45 into 25 into 1571 bracket 0.87 into 500 into 2945 minus answer divided by bracket 0.36 into 25 into so it is coming as 198. Okay, 198 mm square XU. So now what we will do, we will just put it here. 198 minus DC is 50, XU is 198. So epsilon SC is equal to 198 minus 50 divided by 198 into 0.0035. So it is coming as 0.00261. Okay, 0.00261. So for this value we have to calculate the FSC. So how we will calculate? See, 0.00261. So this value lie between these two. So we will write it here, 0.00226, 0.00226, and what is given, 0.00277, 0.00277, and that for value 391.413, 391.3 and 413. You have to find out for value 0.00261. So now we will do the interpolation. See how we can do for FSC. So FSC is equal to this value, this value 391.3 plus 413 minus 391.3 divided by 0.00277 minus 0.00226 bracket into 0.00261 0.00226. So what is coming? It is coming as 399.8. Okay. Newton per mm square. So we can tell it as 400 Newton per mm square. Okay. So what we will do? We will again put the value here, as we have put it here 350. So what we will do? Again we will put the value 350. We will change this to 400. Okay. I am just calculating the value. Xu is equal to, everything will be same, just that part will be changed. See, 400 minus 0.45 into 25 coming into 1571, that is coming bracket 0.87 into 500 into 2945. The XU value is coming as 177.34. So we are taking as 177. Okay. Sorry, it will be mm only. Mm. So you can see it here now that XU limiting is 322 and XU is 177. So you can conclude it here as XU limiting is greater than XU. Okay. So now what we are doing, we can just calculate it from the tension side, but we are doing it from the compression side, as it will be tough. Okay. So moment of resistance, so we will take the XU value only, and that is 177. Okay. Moment of resistance in compression side. Okay. 0.36 FCK XUB. Okay, so this is the force into lever arm D minus 0.42 XU. Okay, so this thing will be same. Now what will come? Plus ASC into FSC minus 0.45 FCK. This is the force into lever arm into D minus DC. Okay, so this is the formula. Now what we have to do? We have to just put the values in it. So see, 0.36 FCK is 25 into XU. XU is 177. B. What is the B? B is 420. Okay, 420. D. D is 750. So 750 minus 50, 700 is equal to 0.42. XU is 177 plus ASC. We have calculated here. ASC is 1571 bracket FSC. So FSC, you see, FSC is 400. This is FSC 400 minus 0.45. FCK is 25. D is 700 and DC is 50. So if you calculate this value, you will sum up to 817.6 kilo Newton meter. This will be the answer. Okay. So we are ending up the lecture here. There is another design of doubly reinforced. We will continue it in the next lecture. Okay.